Use an element argument to prove each statement in 7 through 22. Assume that all sets are subsets of a universal set U. For all sets A, B, and C, A minus B intersection with C minus B equals A intersection C all minus B. So that means we want to show that A minus B intersection C minus B is a subset of A intersection C all minus B, and we need to show separately that A intersection C all minus B is a subset of A minus B intersection C minus D. Now, the way the element argument works is we start with an arbitrary element in the first set, and regardless of the fact that the element is arbitrary, we can still use the definition of these operations involved here to prove that that arbitrary element is also an element of the other set. So let's let X be an element of A minus B intersection C minus B. Now, we don't know what X is. X could literally be any element from the set. But the point is that it doesn't matter what X is. We're going to unpack the definition of these operations here to prove that X must be an element of this other set, A intersection C all minus B. Now, when unpacking operations, you always want to start from the outside in. PEMDAS tells you that you should always do parentheses first, but when unpacking definitions, you want to work backwards. So let's first unpack this intersection operation first. So by definition of intersection, X is an element of A minus B, and X is an element of C minus B. Now we can unpack the definition of set minus. By definition of set minus, X is an element of A, and X is not an element of B, and keep in mind that this and is the same thing as this and. X is an element of C, and X is not an element of B. Now, we really don't need to say that X is not an element of B twice here. Even though it's kind of asserted twice here, when we're explicitly using the word and, it's important not to be gratuitous. It's gratuitous to provide this information that X is not an element of B, since we've already established that X is not an element of B. So really, we could just erase that part and pretend it's not really there. So now we have that X is an element of A, X is not an element of B, and X is an element of C. We want to show that X is an element of A intersection C minus B, which means X is an element of this set and X is not an element of B. We already have that X is not an element of B, so we just need to show that X is an element of A intersection C. To do that, we already have that X is an element of A and X is an element of C. Since X is an element of A and X is an element of C, then by definition of intersection, X is an element of A intersection C. So now we have X is an element of A intersection C and X is not an element of B, which then we can use the definition of set minus again. And so we've shown that X is an element of A intersection C minus B. And so that proves this first part here. Now we have to get to the second part, which says that every element in this first set is also an element of the second set. We will start by instantiating an arbitrary element from the first set. And then we need to unpack these operations from the outside in. So we'll start with the set minus here. So by definition of set minus, X is an element of A intersection C, and X is not an element of B. Now we can unpack the definition of intersection. So by definition of intersection, X is an element of A, and X is an element of C, and we have this X is an element of B. Now, by the idempotent law, we can actually rewrite X is not an element of B twice. So by the idempotent law, X is an element of A and X is not an element of B, and X is an element of C and X is not an element of B. I just added the assertion that X is not an element of B twice. But this is not adding or removing any previous information. We're just restating information so that we can set ourselves up for the set minus operation between these two and these two. So by definition of set minus, X is an element of A minus B, and X is an element of C minus D. And the key here is the word and. We can simplify this statement by converting that and operation into a set operation, the intersection. And so by definition of intersection, X is an element of A minus B, intersection C minus D. And that's what we wanted to show, which means that we've shown that the first set is a subset of the second set, and the second set is a subset of the first set, which therefore means that both sets are equal to each other by definition of set equality. And this is what an element argument looks like. Thanks, everyone, and I will see you in the next video.